my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course.
So now I'm going to go over this very briefly. And so for a chemical reaction, you always add up all the new bonds that are being formed, which is the energy that's being released, and all the bonds that are being broken, which is the energy that's required. So let me write that down for you. So when new bonds form, energy is released. And when bonds are broken, energy is required. So again, this is characteristic of exothermic and endothermic reactions, right? So as an example, let's look at CH2 double bonded to CH2, which is a gas. If you want to know what that looks like, it looks like this. And since you guys have learned how to draw molecular structures, you should have been able to draw this from this molecular formula. Okay, this plus HBr, which is also a gas, you end up with CH3, CH2, Br. So now let's draw out what this guy looks like. So that would be CH2, Br, and CH3. So, okay, what can we look at first? We can figure out which bonds were being broken. So the bonds that got broken is this bond, basically the double bond between the two carbons, and also this bond in order to make this rearrangement, right? And so this double bond was broken and this HBr single bond was broken. This part requires energy. And so the delta H value is going to be positive, right? On the other hand, what new bonds are formed? We formed this single bond between the carbons. We formed a CH bond, which did not exist before because we only had two hydrogens attached, right? And we also made a carbon-bromine bond. So we had three new bond formations in this case. So in this case, the three new bonds releases energy when they're formed. And so the delta H value would be negative. So let's start giving values just so that this makes sense to you guys. So let's say that it requires 612 kilojoules per mole to break this double bond. It requires 366 kilojoules per mole to break this bond. And in order to form some bonds, it requires negative 348 So since I was running out of space, I just redrew this out for you in a more accurate way so you can actually see the energy values that are associated with bonds being broken and bonds being formed. And so to break this double bond, this requires 612 kilojoules per mole. To break this single bond, it requires 366 kilojoules per mole. To form this CH single bond requires negative 348 kilojoules per mole. Remember, since it's releasing energy when the bonds are being formed, it's a negative value. For CC single bonds to be formed, negative 412 kilojoules per mole. And finally, for the CBr single bond, it requires negative 276 kilojoules per mole. All right, and so since we talked about how we can use bond enthalpies and add them up in order to figure out the total delta H of the reaction, right? And so let's do just that. So this is the total of bonds broken, which gives us a value of 978 kilojoules per mole. And let's add up the bonds being formed. and we get a value of negative 1,036 kilojoules per mole. And now all you have to do to figure out the total delta H of the reaction is to add these guys up. So you end up with 978 plus negative 1,036, which gives you a value of negative 58 kilojoules. And so this is an exothermic reaction. The reason why I changed the unit from kilojoules per mole to just kilojoules is because we're assuming we're just working with 1 mole of each molecule. But as you can see, by figuring out the amount of the total energy of the bonds being broken, and then adding that to the total energy of the bonds being formed, this is another way to figure out the delta H of the reaction in addition to Hess's law, which we talked about before.